It is not actually necessary to go through the kernel to get to a device. For some devices, it is possible to configure them to be directly accessed from user level. This method is called operating system bypass. We're bypassing the operating system and from user level directly accessing the device. That means that the device registers or any memory that is assigned for use for this device is directly accessible to the user process. The operating system is involved in configuring this, so making sure that any memory for registers or data corresponding to the device are mapped to the user process. But then after that's performed, the operating system is out of the way. It's not involved in it, and we go from the user process all the way down to the device. Since we don't want the user process to go into the operating system, this driver has to be some user-level driver. It's like a library that the user process has to be linked with in order to perform the device-specific operations regarding the access to registers or device configurations that are typically performed by the kernel-level drivers. Like the kernel-level drivers, this code, this user-level drivers, will typically be provided by the actual manufacturers of the devices. When bypassing the operating system has to make sure that it still has some kind of coarse-grained control. Like, for instance, enabling or disabling a device, adding permissions to add more processes to use the device, etc. This means that the operating system relies on some type of device features. Like, for instance, the device has to have sufficient registers so that the operating system can map some registers to the user process, so the user process can perform the default device functionality like send, receive if it's a network device, or read, write if it's a disk device, but still retain access to whatever registers are used for configuring and controlling the device that are needed for these coarse-grained control operations. If the device has too few registers and it's reusing the same registers for both the core data movement or the core functionality, as well as these control operations that are needed to be performed by the operating system, we can't do this. We need to be able to share the same device across potentially multiple user processes, so assign some subset of the registers to different user-level processes to be controlled by different user-level drivers and libraries, and still make sure that the operating system has some coarse-grained control over exactly how the device is used and whether something needs to be changed. Another thing that happens when multiple processes use the device at the same time is that when the device needs to pass some data to one of the processes, it is now the device that needs to be able to figure out how exactly to pass data to the address space of process 1 versus process 2. For instance, when receiving network packets, the device itself has to determine which process is the target of the packet. If you think about what that means with respect to the networking protocols, that means the device has to peek inside of the packet in order to see what is the port number that this packet is intended to. And then also it has to know which are the socket port numbers that these processes are using in their communication. So what that means is that the device has to perform some protocol functionality in order to be able to demultiplex the different packets that belong to these different processes. In general, it needs to have demultiplexing capabilities so that data that's arriving at this device can be correctly passed to the appropriate process. In a regular device stack where the operating system kernel is involved, it is the kernel that performs these operations. The kernel is aware of the resources that are allocated to each process and the mappings that each process has with respect to the physical resources in the system. When the operating system is bypassed, those types of checks have to be performed by the device itself.